All right. Hi again, everyone. So this time we're going to be talking a bit about group actions, so roughly corresponding to Chapter 5 of Goodman. That's what we're going to be doing over the next little while. So we're going to be discussing the basics of group actions, which we actually know about already, but I'll quickly review them. And then we're going to get into some interesting kind of counting theorems. And then we're going to talk about group actions on groups and how that leads to a lot of interesting structure theory for groups, some versions of which we've already seen. So let me recall the basic definition that we already know. The camera's kind of funny today. Let me maybe change my position here. Okay, so definition. So this we've seen before. So if G is a group and X is a set, then an action of G on X is simply a group homomorphism. So is a group homomorphism, group homom, and what is it? From G to the symmetric group on X. All right, so we've discussed this pretty extensively. I'll just say, in a quick parenthetical, that this is equivalent to specifying a map from G cross X to X, such that G1, G2X. So this map will be called G dot X. So that's very typical notation, and such that G1 times G2X evaluated this way is G1, G2 evaluated this way dot X, like that. Okay, so I've discussed that in class a bunch about why that's the same, so I won't say the details again, but well, maybe I won't write the details, but I'll say the details. Let's compromise that way. So the point is that how do you get this map? You take an element of G, and that yields an automorphism of X, right? So for any G and G and any element X and X, I can take the associated automorphism via this map and evaluate it on X, right? So if this map is called A, okay, I'm semi-compromising even more and writing it a little bit, then this G dot X, you could also write it as A of G. That's a map from X to itself, and you can then evaluate it on X, which lives inside X, right? So that gives you G cross X to X, and then the fact that the thing is a group homomorphism gives you this. All right, now I'll really stop proving it again. Okay, and we've seen lots of examples of group actions, right? So already we've seen that group actions can yield interesting structure theory for groups. So let's recall that we proved the famous Lagrange's theorem this way. So if H is a subgroup of G, we have both the left and right actions. Well, okay, I haven't said what a right action is. It would just be the same thing, but where the order of multiplication is reversed. So you have the group action of H on G. So the group action, which is H cross G to G, and it's given by H comma G is just H times G, the multiplication in the group, right? So anytime you have a group, and of course H could be equal to G. So anytime you have a group, you have an action of the group on itself. Anytime you have a subgroup, you have an action of H on the group. And then the important thing about this was to look at the orbits. So this is a convenient spot to recall that definition. So let's recall that what the orbits are. So an orbit, so the orbits of G on X are the subsets of the form. So there are a bunch of subsets of X, and which ones are they? They're, let's say, yeah, no, that's fine actually. Little y in X, such that y is in G times little x for a fixed little x in X. So for some x in X, right? So in other words, you have some element of X, and what is an orbit? An orbit is all the things that you can obtain from it by multiplying by G. So you do all possible multiplications. That gives you a bunch of other elements of X. That is a set of that type is called an orbit, and then the orbit's partition the orbits partition the group G into a disjoint union of subsets. So in fact, so we proved all this already. So I'm being a little bit terse, a little bit brief, but okay. So in fact, the relation x tilde y, if and only if x is in G times y, is an equivalence relation on x. Okay, so we reviewed that, and if you don't recall the proof, I would encourage you to write it out again. It's an easy, just try to work it out. It's an easy exercise involving the properties of multiplication and inverses of G. So this is an equivalence relation on x, and the orbits are just the equivalence classes. So here's, in fact, another definition of orbits, which is maybe even better than the first one. The orbits are just the equivalence classes under some relation. Okay, and so equivalence classes are always good to have. They always take a set and partition it into a disjoint union of subsets with nice properties, right? We've seen that. Okay, so all right, so that's very good. And then what was the point for Lagrange's theorem? So the point for Lagrange's theorem was that, in fact, so in the case of the regular action of a left action of a subgroup on a group, these orbits all had the same size. So we've already seen an example of some deep structure theorem from group theory coming out of this. So if G is finite, and H and G, sorry, that was kind of wonky. If G is finite and H is a subgroup of G, then the orbits of H on G all have the same size. Namely, the cardinality of H, right? So if G is a finite group, H is a subset of G, so it's a finite set as well. And then if you look at that left action of H on G, that partitions the set G into these equivalence classes, just as we described here. And what we proved, the lemma that we proved from weeks ago, was that all of the orbits have the same size, namely the cardinality of H itself, right? So I'm writing this absolute value of H. I think the other day when I was talking about numbers, I wrote this number of elements in H like that. So I'll write both. Doesn't matter. Either way, the same. Okay. And right. And so what's the proof of this? The point is that each orbit is the set of things of the form H times something. But then, how many things are there like that? Exactly H distinct things, because H is a subgroup of G, and so you can't have two things being two different elements of H giving you the same element. In fact, I'm being a little bit vague here. One, because we already proved it in class before, and two, because we're going to talk about a number of counting and orbit formulas today, in the next couple lectures, which will include this as a special case. So I'm not going to try to write a proof of this now, just because we've already known it, and it'll be easy again in a minute. And so let's recall that this implied. So recall that this implied that the order of H divides into the order of G, because G itself now can be partitioned into a disjoint union of subsets, all of which have the same size, namely the integer H. Okay, so this is a powerful structure theorem about finite groups that drops out right away from basic facts about orbits, and it turns out that a lot of interesting kind of combinatorics and counting and other interesting things come out of this. So we're going to be talking about that a little bit, as well as interesting structure theory for groups, of which this is only the very tip of the iceberg. Okay, I'm trying to think of other basic examples of actions that I want to do. Oh yeah, right. So Goodman talks a bit about the conjugation action. The conjugation action is also very important. So let me give you one more example to follow. Again, this is a similar to Goodman chapter 5, chapter 5.1. I'm not deviating too much here, so you can look this up there as well. So so there's another action of G on G, which is given by conjugation. So the map from G to sim G, which takes an element little g. Okay, so I have to take an element of G and produce a map from G to itself. And so that map is going to be x goes to gx G inverse. So this is called conjugation. And so you've seen conjugation in life before. We talked about it, I guess, a little bit maybe in the symmetric group, but the most important place that you would see it is in linear algebra, where if I have two different matrices, invertible matrices, they're conjugate if and only if they represent the same linear transformation in different bases, right? So the conjugation relation in linear algebra precisely means that there's a change of basis in some vector space for the same linear transformation. So this is a very important fact you can look it up in Friedberg, Inzel, and Spence chapter 2, 2.6, I think, if I recall correctly, 2.5, something like that. But it's a basic operation in linear algebra for that reason. Okay, and so the point is that this is actually a group homomorphism. So this is a map from G to itself. It's not either left or right multiplication, right? It's something different. And the point is that this is a group homomorphism. So so this is a group homomorphism because GH now goes to the map X goes to GH X GH inverse, which is G. So just massaging the parentheses a little bit, right? I can flip the order of G and H here, which is this. And so this is the conjugation by H on X followed by the conjugation by G on X. So let me maybe I'll follow Goodman's notation and give this the name C sub G of X. So I was going to avoid writing that, but actually it is useful. I take it back, it's useful. So so G goes to a map C sub G, which is GX G inverse. Okay, and then writing this way, so this is exactly C sub G of C sub H of X, right? So we see that GH goes to CG of CH, and so this is a group homomorphism. And so this implies that this is an action, because it respects the group structure on G and on sim G. Sometimes, of course, it's very trivial, right? Like, for instance, if G is abelian, this does nothing, right? GX G inverse is always X. But if G is not abelian, this is telling you interesting things, and we'll return more to it as we go along, and especially when we do structure theorems for groups and all that kind of good stuff. Okay, so that's an important example to discuss. Yeah. Okay. Very good. Yeah. Okay. What are the other basic definitions I want to give you here? I want to give you stabilizer, and then I want to talk about some counting. So let's do that. So that was mostly review up till now. Now here's a new definition. So definition, let G act on X, and let little x live in X. Then we define the stabilizer, stab G of X, or just stab X, depending on the context. Sometimes you put the G in, sometimes you leave it out. And this is going to be the set of all G and G such that G times X is X. Okay, so it's the set of stuff that fixes that little x under G. Okay, and this is a subgroup. So stab GX is a subgroup. So in fact, yeah. So lemma. Stab GX is a subgroup. And there's a bijection so on the one hand, I take G mod stab G, so it's a subgroup, and so of course I can take G and quotient out by just take the set of equivalence classes with respect to the left multiplication by stab G, so that's a quotient set of G, and that goes in bijection onto this O of X, the orbit of X, right? So this is Y in X such that Y is in G times X. So there's a close, tight relationship between the stabilizer and the orbit Namely, if I take G and I quotient out by the stabilizer, take the quotient by that relation, I'm actually in a bijective relationship with the orbit. Okay, so what's the proof of this lemma? So, all right, so the fact that stab is a subgroup is a pretty easy exercise, right? So we need to check that. So for stab being a subgroup, so let's call these things 1. No, actually I won't do that. So to check stab as a subgroup, I'm just going to note that GH times X is G times H times X, right? So if G and H are both living in stab, or maybe say it this way, GH both living in stab imply, right? If things are all living in stab, then they are fixing X. So that's X and then that's X. So that implies GH times X is X, implies GH in stab. And G in stab implies GX is X, implies G inverse X is X, right? Because I can left multiply this equation by G inverse and get X, and then that would be G inverse times X, right? So if I have a relation like this, I have the same relation the other way, multiplying by the inverses, right? So that gives this, and so that gives G inverses, right? Okay, so it's a quick check that it's closed under multiplication, it's closed under inverses. So it obviously is non-empty and contains the identity, right? Because the identity times X is always X. So okay, so stab being a subgroup is very simple. And now what is this bijection from G quotient out by the left multiplication by stab with O? So I'm going to define a map. So now we define a map from G to OX, and it takes any little element to G times X. Right? So there's always a map, right? Once I fix an element, little x, in big X, then there's always a map from G onto the orbit, because I can take an element of G and just multiply it by that little x, and by definition that gets me into the orbit. And in fact, the orbit is all the things of the form G times X. So this is clearly onto. Right? There's nothing to say to prove that it's onto. It's just literally the definition of orbit. Now it's not necessarily one-to-one. To make it one-to-one, instead I have to correct. So what I have to show you is that two elements of G go to the same element of O if and only if they tilde each other under multiplication by stab. So what do we need to show? So it's not one-to-one, but it can be corrected to be one-to-one after sort of modifying by an equivalence relation. Right? So what do we need to show? We need to show that G1 and G2, let's call this map something. Let's call it capital Phi. So we need to show that phi of G1 equals phi of G2. That happens if and only if, now if it were one-to-one, I would say if and only if G1 equals G2. Since it's this different thing, I'm going to say, where is it? Since it's this, I'm going to say if and only if G1 tilde G2. And now to review, what equivalence relation am I using? I'm using if and only if G1 is in stab GX times G2. Right? So if and only if G1 and G2 are in the same equivalence class under left multiplication by stab G. Okay, so there's two directions. Let's suppose that phi of G1 is equal to phi of G2. So let me give you the first direction. Suppose this way. Suppose phi of G1 equals phi of G2. So that's the same as saying that G1 times X equals G2 times X, right? These two things are equal. Okay, so that's the same as saying, I guess, that G1 inverse G2 is in stab GX, right? Because if I left multiply by G1 inverse, then I get that G1 inverse G2 fixes X, right? But then this is the same as saying that G2 is in yeah, it doesn't, I mean, I could have done it either way, I guess. G2 is in Yeah, it's in the it's in the yeah, it's in G1 times stab x. So I'm sorry, I wrote this equivalence relation the wrong way. Oops. Let me make sure to correct that. Yeah. Okay, sorry. So I wrote it the way that I originally thought it was written was it as in terms of the left multiplication by stab x, but in fact it has to be the right multiplication as the proof clearly shows. So, and in fact, Goodman's proof is the same thing. Okay, all right, whoops. So it doesn't really affect the statement, but I have to now be clear that I mean this is not the left multiplication, but the right, not the left quotient, but the right-handed one, right? You can instead of doing everything with left multiplication, you could do it with right multiplication, and the definitions all make sense. So let me note that this is the right multiplication by stab. So this is the quotient where the equivalence relation is given by the right multiplication by stab gx. Okay, so as opposed to the left, which I was implicitly assuming it was, but that's clearly wrong, because now when we look at the proof, let's look at it. We get G1 inverse G2 is in stab G, and that's the same as G2 is in G1 times stab Gx. So for a non-abelian group, these two relations will be different. There's the one where you say two things are related if they're in the left multiplication by the group, and the other if they're related in the right multiplication by the group. So they're both perfectly good definitions, and they work the same way, but you have to pick which one you're going to do. Okay, so so that gives us that way. And for the other direction, it's exactly the same thing, right? G2 is in G1 times stab Gx. In fact, I could have really done it this way as well. It implies G1 inverse G2 is in stab Gx, which implies G1x equals G2x, which implies phi of G1 equals phi of G2. Okay, so I wrote this twice when I didn't have to. I mean, it's exactly the same proof both directions. Okay, so it's naturally in bijection with the right cosets of the under multiplication by the group stab. Okay, so in the interest of general video timing, I'm going to stop now, and then I'll return later with another 20-25 minute video, just because I don't want to keep trying to upload these enormous 50-minute videos. It's technologically annoying. So I will be back with the second round of this lecture later on today.